Nice to meet you. I'm Khadan Choktai and you're watching my YouTube channel School of Advanced Chemistry. I'm going to explain KSP, constant for the solubility product for A2 chemistry students. Let's get started. KSP, K capital KSP in subscript. Basically this K is equilibrium constant. K is the equilibrium constant and SP stand for solubility product. This expression is used to check the solubility of a sparingly soluble compound or less soluble compound. KSP, this expression is used to know the solubility of less soluble or sparingly soluble compound or sparingly soluble hydroxide, for example, into the water. So basically the compound, those are not fully ionized in water. We cannot judge, we cannot guess, we cannot assess their extent of ionization, their extent of solubility. So first of all, we are going to calculate KSP. It will tells us its solubility. I mean, solubility and KSP are highly interrelated to each other. Solubility of a compound and its KSP value or its KSP answer are interrelated to each other. They are, with the answer of KSP, we can find the solubility of that compound into the water with respect to mole per dm cube or in mole per dm cube. If the solubility is known, then we can find its KSP. So once again, KSP is an equilibrium constant that is showing the basically product of soluble ions. So solubility can be converted into solubility product, and solubility product can be changed into solubility. We can find the answer of solubility if the KSP is given, and we can make the expression of, or we can calculate the answer of KSP if the solubility is given. Now let's see what the KSP is and how to write its expression. Basically, KSP, if I'm having PbCl2, it is basically a less soluble, or you can say almost insoluble compound. If I'm going to dissolve it into the water to make a saturated solution, when equilibria is established, initially it is going to dissolve into the water to make ions Pb2 positive, lead2 positive ion aqueous, plus 2 mole of Cl negative ion aqueous. Then a time will come, then these ions will get together, will meet together to make PbCl2 solid back. This is forward reaction. After some time, there is commencement of the backward or the reverse reaction. A time will come when the rate of forward reaction is equal to the rate of reverse reaction. This is called dynamic equilibrium. And now the solution, this one solution has been saturated with PbCl2 ions. Lead2 positive ion and Cl negative ion. So at this time, at this stage, the expression of Kc, we can write the expression of Kc over here. What is the expression of Kc for this reaction? Concentration of product or the species present on the right hand side, that is Pb2 positive, and what is its mole? There is 1 mole raised to power its mole. Product multiply by the concentration of the second ion, that is Cl negative ion, raised to power its mole is equal to 2, so raised to power 2, divided by concentration of main reactant, but it is very much less soluble, almost it remain undissolved, so its value will remain constant. If its value is going to be constant and it is a solid, so I'm going to take 1. I'm not going to take any other value. I'm not going to take the PbCl2 concentration over here. So its concentration will remain 1, it's constant. This Kc is basically, in fact, it's named or it's termed as KSP. K equilibrium constant are the ratio of the product and the reactant at equilibrium, and SP mean solubility product. This is the product. Multiplication of the two things is called product, and these ions are because of the solubility of the compound. So product of the positive and negative ions, those are formed because of the solubility. They are said to be solubility product. This term is said to be solubility product. So this Kc, in fact, that is named as, the other name of this Kc is equal to KSP, and it is having no denominator or one denominator, I mean. So I'm going to write it again. KSP is equal to concentration of Pb2 positive, this bracket mean concentration in mole per dm cube, into the concentration of Cl negative ion raised to power 2. This is the true expression for the KSP of this K1 reaction or K1 compound. This is the basic true expression of solubility product of PbCl2. Now similarly, if I'm going to write this expression in term of X, what is this X? I am going to take the supposed answer or supposed value. For example, I am going to dissolve PbCl2 into the water. So solubility in water. Solubility of PbCl2 in water. PbCl2 again goes to reversible arrow. Pb2 positive ion aqueous, 2 mole of Cl negative ion aqueous. For example, if I'm going to take initially 1 mole of PbCl2 and I'm going to dissolve into 1 dm cube water. 1 dm cube water, in 1 dm cube water I'm going to dissolve 1 mole of PbCl2. Initially, at the time t is equal to 0, it is not, it is just going to dissolve. At the moment, there is no concentration of Pb2 positive ion, there will be no concentration or zero concentration of Cl negative ion. But when the equilibrium has been reached, at the stage of equilibrium, when saturated solution has been formed, at that time its concentration will be 1 minus X goes to, its concentration will be X mole per dm cube, per 1 dm cube, these are the mole basically, and X mole 2X will be the mole of Cl negative ion, or 2X is the mole per dm cube, that is the concentration of Cl negative ion. So in term of this shortcut you can say, or in term of X, what is the KSP, or what is the expression of KSP? So KSP is not going to have any reactant. KSP, in the expression of KSP, there are no reactant. Instead of reactant, we are going to write just one, putting 1 over here. We are just having product. Let's see over here. Pb2 positive ion concentration multiplied by Cl negative ion concentration raised to power 2. What is the answer of concentration of Pb2 positive ion in term of X? That is X. So X multiplied by, what is the concentration of Cl negative ion in term of X? That is 2X, and raised to power 2, that is lying in this formula. So what is the answer? The KSP is equal to 4X cube. So this is the new expression of KSP in term of X. What is this X? Why I drive this expression of X? Basically, this X is solubility. Solubility, and its unit will be mole per dm cube. X is the solubility. Whenever you are supposed to find the value of X from KSP, you will use this expression. Or the X is given, I mean if the solubility is given and they are asking to find the value of KSP, you will again use this expression. So this is the X. X means solubility, amount of solute that has been dissolved, that has been minus from the original value, and this quantity has been ionized into the water. So X is the solubility, mean whenever they are asking to find the answer of solubility, you will find the answer of X. And if X is given, then they may ask to find the answer of solubility product. So solubility product is this one, and in term of X it is this one. So whenever they are asking to find the value of solubility product, you may use the value of X. Now, the next thing is, what is basically solubility product means? Solubility product mean the value that is the multiplication of positive and negative ion, a constant value that is constant at room temperature. I mean, if the temperature is constant, KSP is a constant. K for constant, and it's a constant if temperature is constant. If temperature is constant, K will remain constant. Let's see how to calculate solubility from the KSP data. I mean, once again, I'm having this PbCl2 that is going to be solubilized in water. And this is the answer of its KSP. And I am supposed to find the answer of solubility in water. Solubility of PbCl2 in water from KSP. I'm going to find it. Let's see over here. I'm going to write the expression of KSP in term of X. So at the stage of equilibrium, it will be X mole. There will be 2 mole of X for Cl. And in expression, you know that Pb 2 positive ion concentration and multiply by Cl negative ion concentration raised to power 2. So the concentration of Pb2 positive ion in term of X is equal to simply X multiplied by Cl negative ion concentration is 2X raised to power 2. So in term of X, its answer is 4X cube, and that is equal to KSP. What is the answer of KSP? You know, the answer of KSP is equal to 2 into 2.0 into 10 raised to power minus 5. So 4x cube is equal to this answer. And what is X? X cube, let's suppose that is equal to 2.0 into 10 raised to power minus 5 divided by 4. And taking cube root on both sides, I mean, we can see it over here. The value of X will be equal to 0.0171. And this is, as I told you, X is the solubility. So this is mole per dm cube of PbCl2 at the moment under normal condition at room temperature in water. So this is the solubility of PbCl2 in water under normal condition of temperature and pressure. So that is the solubility. Now let's see over here. We can also calculate the solubility of a compound into another aqueous solution, in aqueous solution, not in water. Basically, for example, I mean solubility in an aqueous solution. Solubility in an aqueous solution mean, for example, I am going to dissolve some PbCl2 into 0.1 mole per dm cube of NaCl aqueous solution. This time I'm not going to dissolve PbCl2 into the water. I'm going to dissolve PbCl2 into 0.1 mole per dm cube of NaCl. So what will be its solubility? Obviously, its solubility will be less than that of this one, because NaCl is also having the same ion, Cl negative ion, that is present in PbCl2. And the reason is these two common ions will basically repel each other, and there will be a common ion effect. So how to find the solubility in this case? Number one, NaCl is more soluble than PbCl2, so I'm putting this one arrow and I'm going to write Na positive ion and Cl negative ion. But in case of PbCl2, that is going to make Pb2 positive ion and 2 mole of Cl negative ion. In both cases, we can see that they both are happening in the same container, in the same solution, in the same beaker, I mean. So what is the concentration of PCl over here? So overall, we need the concentration of Pb2 positive ion. What will be the concentration? Let's suppose it is X concentration, X mole of Pb2 positive ion. And in terms of X, I mean, what will be the concentration of Cl negative ion? That will be, that is the 2X, as we have seen in previous example. But this time from this Cl is also coming from NaCl, and its concentration is equal to 0.1 mole. So the concentration of Cl negative ion is equal to 0.1 plus 2X. That is the new concentration of the Cl negative ion in this beaker, and X is the concentration of, or the solubility you can say as well. X is the concentration of ion as well as the solubility of this compound. Both are X basically. So now I'm going to put the value of Ksp and using the same formula. So once again, Ksp is equal to Pb2 positive ion concentration multiplied by the concentration of Cl negative ion raised to power 2. Here the Pb concentration is equal to X, and multiplied by this Cl concentration of the Cl negative ion is this one, 0.1 plus 2X raised to power 2. But here I'm going to apply an approximation. The approximation is this one, as this 2X is, this value is, this especially this X is very much low. So I'm going to neglect this concentration of Cl negative ion that is coming from lead chloride. This 2X that is coming from the PbCl2 will be very much in less quantity, so I'm going to ignore this concentration, and I'm inputting 0.1, or you can say I am taking 2X is equal to 0. It is said to be approximation. So finally, X multiplied by 0.1 raised to power 2, and here is the answer of Ksp, that is 2 into 10 raised to power minus 5. Now the X will be equal to 2 into 10 raised to power minus 5 divided by 0.1 square. And what will be the answer of X? So the answer of x is equal to 2 into 10 raised to power minus 3. This x is the concentration of Pb2 positive ion, yes. And similarly, this x is solubility. Solubility is also equal to x, and this x is also the concentration of Pb2 positive ion. So in this case, we can find the solubility of a compound in any other saturated solution. So initially in water, PbCl2 solubility is this one, 0.0171 mole per dm cube. But in case of NaCl solution that is already present in the water, and if I'm going to dissolve this PbCl2 into that, at that time at room temperature, the solubility will be equal to 2 into 10 to the power minus 3. So that is the method how can we find the solubility of any less soluble compound in two different scenarios. The next thing is predicting the precipitation. With the help of the value of Ksp, we can predict the extent of solubility. Predicting the precipitation. Basically, with the help of Ksp answer, the value of Ksp also tells us the extent of ionization or the formation of precipitate. Extent of ionization of the value of Ksp tells us extent of solubility, extent of solubility, or you can say the formation of precipitate. Ksp is the limit of solubility of two ions. One is the positive ion and other one is negative ion. When the answer of the product of these concentration of these two ions is going to exceed from the value of Ksp, then there will be no more solubility and precipitate will form. For example, I'm having two beakers. In one beaker I'm having NaCl, that is 0.1 mole per dm cube. In another beaker I'm having PbNO3 twice, lead 2 nitrate, and its concentration is 0.1 as well. So I'm going to mix these two beakers, two solution basically over here. In this solution, let's suppose, for example, the concentration is not going to change. The concentration of Pb2 positive ion is equal to 0.1 and concentration of Cl negative ion. Concentration of Pb2 positive ion is equal to 0.1 and the concentration of Cl negative ion is also equal to 0.1 mole per dm cube. Now I'm going to find new Ksp answer, that is called ionic product. I'm going to find the new answer that is said to be ionic product. Ionic product. Pb, the same formula as that of Ksp, 2 positive ion multiply by, here is the formula of Cl negative ion raised to power 2. In this case, the concentration is 0.1. Here now the concentration is given And here the concentration is also equal to 0.1 raised to power 2. So what will be the answer of this new ionic product? The answer is, generally speaking, uh, 0.1 into 0.01. 0.1 into 0.01. And the answer is 1 into 10 raised to power minus 3. So 1 into 10 raised to power minus 3. This is the answer. And you know what is its solubility product, Ksp? The value of Ksp is equal to 2 into 10 raised to power minus 3. So in this case, the answer of Ksp is bigger than the answer of ionic product. So this concentration will remain soluble. If the answer is not exceeding, the answer of the ionic product is not exceeding this limit, the limit of Ksp, then it means that this compound will remain, this mixture is going to be soluble for PbCl2 or Pb and Cl negative ion. Similarly, if I'm going to add another mixture, I'm making another mixture in which the Cl negative ion from NaCl is equal to 0.2 mole per dm cube, and from Pb2 positive ion, the concentration of Pb2 positive ion is 0.1 mole per dm cube. Similarly, the concentration of Pb2 positive ion 0.1 multiply by, I'm going to find the ionic product and multiply by the Cl negative ion 0.2 raised to power 2. So 0.1 multiplied by 0.2 square. The answer is 0.04. 0.04, and the overall answer is 4 into 10 raised to power minus 3. 4 into 10 raised to power minus 3. Now you can see that this answer is bigger. The answer of ionic product is bigger than that of Ksp. So there will be precipitate. Precipitate will formed. I mean, if the answer of the Ksp is higher, then there will be no precipitation after the mixing of solution. If the answer of the ionic product is bigger than Ksp, then there will be the formation of precipitate. Now the basic and important thing is this one. These two are not the same concentration. Their sources are not same. It's coming from NaCl. Cl negative ion is coming from NaCl. Lead nitrate is a source of Pb. So the source of Pb2 positive ion and the source of Cl negative ion are not same, and their values are not same. But whenever they are going to meet the answer of Ksp, then precipitation starts over there, and that is explained by the answer of Ksp. That is another application of Ksp. So this is the basic theme of Ksp, application of Ksp, and there are some limitation, or you can say requirement for the Ksp. Number one, the Ksp theme is applicable only for saturated solutions. If the solution is not saturated, if the compound is not less soluble, is fully soluble, then Ksp is not applicable. Ksp is applicable when the solution is going to be saturated, compound is less soluble. If the compound is less soluble, or not fully soluble. So Ksp is applicable for less soluble compound, not for the complete soluble compounds. So that is one of the basic limitation you can say of the KSP. Now the next thing is, as I told you, KSP is the equilibrium constant. Yes, K is equilibrium constant, and like Kc, it is going to be constant if temperature is constant. It is constant if the temperature is constant. If temperature is not constant, it will no more be constant, and so on. That's all about this topic. Thank you very much. Please subscribe my channel, hit the bell icon, and share it with your friends. Thank you. Thank you very much. Have a nice day.